Okay, so we want to know if we can't get 100% efficiency, how good can we get? And that brings us to the Carnot cycle. So the Carnot cycle is based on a theoretically perfectly reversible heat engine, and it would be the most efficient that you could get for any particular thing. So Carnot efficiency is always the maximum efficiency you can get for anything. And you can see here in the Carnot cycle, we start here and we only use isotherms and adiabats. Okay, so we only use isothermal processes and adiabatic processes, and these things can go either way. So here we have our first isothermal compression. So isothermal compression means that we have QC going out, okay? Then we have an adiabatic compression, which has no exchange of heat. Remember, Q is 0 for adiabatic processes. Then we have an isothermal expansion, so we have heat going in, and then we have another adiabatic expansion, and that means there's no heat exchange, okay? So we drew it one way, but we could definitely draw it going the other way because all of these processes can be reversed. So Carnot is the same as reversible, and a Carnot engine with the same hot and cold reservoir temps will have the same efficiency all the time. All right, so here is the equation for the efficiency of a Carnot engine. And as you can see, it's just 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. Okay, to get 100% efficiency, this has to go to 0. So the hotter you can make your hot reservoir, the closer you can get to 100% efficiency. But since we know this can never be exactly 0, because this always is a non-zero quantity, and this is always going to be a non-zero quantity, this means this is the best efficiency you can get, and it's never going to be 100%, so it doesn't violate the second law of thermodynamics. So another statement of the second law is that no heat engine operating between TH and TC can exceed the Carnot efficiency. All right, so here we can go through and calculate the Carnot efficiency from the Otto cycle engine from the previous example. All right, so we know that thing operated between temperatures of 273 and 1770 Kelvin, and it had a theoretical efficiency of about 60%. Okay, so the maximum efficiency this engine could have, if you adjust it to all the best parameters, is going to be the Carnot efficiency. Okay, maximum efficiency is also always the Carnot efficiency. So we plug those numbers in, and we get about 84.6%. Okay, and so this means that the maximum efficiency you could ever get from an Otto cycle engine with these temperatures is about 85%, and that's bigger than the 60% we actually got. Okay, so can this heat engine be built? I'm going to give you a couple minutes, pause the video, see if you can figure out what you think. All right, we're back. It turns out the answer is no. Now, why is the answer no? Well, what's the Carnot efficiency? All right, Carnot efficiency is going to be 1 minus TH divided by TC. Okay, well, or sorry, TC divided by TH. So 1 divided by TC divided by TH. TC divided by TH, that's 300 over 600, that's 1/2. So 1 minus 1/2, that's 1/2, that's 50%. Okay, well, if you look at the efficiency, that's going to be the work over the heat. So that's going to be 60 joules over 100 joules. So 60 over 100, that's 60%. 60% exceeds the Carnot efficiency of 50%, and therefore you cannot get this efficiency. This heat engine is not physically possible to be built. It violates the second law of thermodynamics. And just for some context, here's some real life efficiencies, okay? So for a coal-fired plant, and for this specific coal-fired plants in the UK, the Carnot efficiency is about 64%. The actual efficiency of the plant, 36%. Okay, remember this one's just based on the hot and cold reservoirs. This one is what's actually observed. Okay, here's a Canadian nuclear power plant. Its Carnot efficiency based on these temperatures is about 48%, observed at 30%. Here's a geothermal power plant. Carnot efficiency is 33% based on the temperature difference, and observed is about 16%. And if you want to check this out, you can find this data on Wikipedia under heat engines. All right. Heat from fossil fuels. Hydrocarbons are burned with oxygen. They give off heat and energy. Here's some of the processes that go through that. All right.